Hello everyone. So today we're gonna we have a case history. The case history is a very large retaining wall in Seattle, and then after that we will talk about effective stress, a very important concept in soil mechanics. So let me turn off the lights, and then we'll do the. The printer, laser, there we are. So this is a 46-meter high mechanically stabilized earth walls, and you'll understand what that means, for the extension of, for being able to build a new runway in Seattle Airport. The date of construction is the year 2005. So 46 meters, that's about a 15-story building. So it's a mighty high, it's a record high wall. So these are the credits to the Reinforced Earth Company, RICO, and others who contributed to publishing this huge project. So we're going to Seattle. And it's the SeaTac Airport, Seattle-Tacoma. And you see here that there is a number of runways on the airport. They wanted to extend and create another runway because of increased traffic. Here is the view of the airport. So they had a number of runways and taxiways. They wanted to build one more runway on the outside to handle additional traffic. The problem is, as you may know, Seattle has a lot of mountains and valleys, and so the terrain was not flat, and there was a need right here. There was a big valley with a creek going this way, so there was a need to build a big wall to be able to handle to place the runway here. So there was a west wall and the north wall, which was at the end of the runway. The big one was the west wall. So remember, west wall is the one we're going to be talking about. I'll show you the wall construction because it's really a specific type of wall. You know, when we think of retaining wall, we think of a wall made of concrete, and then behind that concrete wall, we place the backfill. This is not the way this works. You can see here that we have a number of steel strips, and then we're going to cover this with backfill about 30 centimeters, and then after 30 centimeters we want to place another layer of steel strips, and then backfill, and then steel strips, and then backfill, and then steel strips, and we're going to go up all the way to the top here where we need to end up. And that's called reinforced earth, and more recently the word is mechanically stabilized earth wall. If you wish, in a way it's to soils what reinforced concrete is to concrete. You know, concrete is relatively weak in tension compared to its compression ability, and so a long time ago, about 1910 or so, folks started to put bars, reinforcing bars in concrete, and that's what led us to reinforced concrete design. So this concept started in around 1960 in soils, where this fellow Henri Vidal, a French guy, that had the idea of extending, if you wish, the reinforced earth concept to soil reinforcement. And so you build the wall like this. By the way, so Henri Vidal patented his invention. The story goes that he was on the beach and he was playing with pebbles and then placing a sheet of paper, then pebbles, then paper, then pebbles, and so on. And he thought, goodness, I can really pile up that stuff pretty high. Maybe I should think of doing that in the soil. And he did, patented his idea, and fought fought the patent, and because every time you have a good idea, you can be sure people are going to copy it. And they're going to try very hard, and so you have to defend your patent in the court of law. Anyway, so that's how you build an MSE wall. You can see here the strips, the end of the strips. The front of the wall is right here. So you place those wall panels, and then you lay down the strips. They're going back all the way here. And then you put a layer of backfill on top of that. And once you've done this, you put another layer of strips on top of it that you hook up to the front panels, and then layer of soil, and so on, and you go up that way. So here are the connections for the strips. So there would be soil placed up to the level of the strips, then the strips would be laid down, and then soil and strips and soil and strips and so on. And here's the wall completed. And the reason these wall types have been very successful, again started in 1960, is because they are less expensive than the typical. If you wanted to do a wall like this by doing a concrete facing all the way up, that would be a massive piece of concrete with a foundation and so on. So these walls are self-sustaining, and also they are quite resilient in the sense that, you know, Seattle is in an earthquake area, and they're very resilient when subjected to earthquake. They deform relatively easily without breaking, if you wish, and so they're ductile. They're not brittle, they're ductile. So here is, and you can imagine that being in Seattle, you had to put a Seahawk here as a design for the wall. So extensive, let's go back. I showed you the construction because the type is important and how it's built. But to start the project, you can see the creek is here. A lot of geotechnical investigation, borings to find out what the soil is like. And because this huge mass of soil that you're going to build in that valley is going to actually compress the material underneath. And so there is a need to find out what it's like. One of the things that's very important, and you will run that test in the lab, is the direct shear friction angle. And basically what that is the friction, to find out what the friction coefficient is for the soil grains when they rub against each other. And it was important to have a minimum, and this is fairly high. I think the design value was, well, the mean was 41, but the design value had to be 36 or 37. Anyway, so this is a direct shear test that we run on sand, and you will do that. So for this project, there was a fair amount of numerical analyses that were done to find out how it would deform, the stresses, the settlement. The wall design included finding out how strong the panels had to be. These are the galvanized steel strips. They're 6 millimeter thick. So you might think, well, that's not very thick, but if you look at the load that's in the strip divided by the area, you find out that you don't need 6 millimeters. In fact, you need quite a bit less. But the strip is made that thick to be able to handle corrosion. In other words, there is a sacrificial thickness in the strip to be able to handle corrosion, and also the steel is galvanized. In terms of instrument, because this was a record height, the constructor decided to instrument this soil mass, reinforced soil mass, with a number of instruments, and we'll see what they gave in the end. Note here, you see that dashed line that's right there. That's the zone where the soil is transferring the stresses that it's feeling, having to stand up all by itself, or having to stand up that high, 46 meter high, transferring those stresses to the steel reinforcement. So because this is essentially the load being developed in the seal strips. You cannot count that length as a resisting length for the strips. So you have to neglect that zone, and then you can start counting how long the strip has to be behind that zone. So this is the instrumentation. You can see the strip. This is not to scale, by the way. Well, maybe it is. Anyway, so instrumentation. You see strain gauges on the reinforcing strips, inclinometer, and then the survey points to find out how much the wall is moving up and sideways. This is another cross section. You can see that it's not an exactly straight up wall. There are tiers, step back tiers of the wall. So overall, the west wall, remember the west wall is the one that was the big one. 10 to 74 millimeters of lateral movement, about 86 millimeters, maximum 155 millimeters of settlement, and then strain gauges and stress and so on. So let me show you here. You see here the load in the reinforcement given by the strain gauges, and you see that wedge that I was telling you about. So the load is transferred and then it decreases because it's absorbed by the reinforcement pulling on the soil that can resist it. This is settlement. So the settlement of the wall was of the order, you can see it here, of the order of about 200 millimeters after about 2 years. So it took about, so 200 millimeters, that's 8 inches. So it's a fair amount, it's probably the length of your hand expanded. But as I said, these walls are quite flexible, and so they could handle this kind of settlement. And here is the settlement in millimeters. You can see around 200 millimeters here at the bottom. This is the lateral movement. So sideways, the wall moved about 90 millimeters, 4 inches. Because you have to have deformation in order to transfer the load from the soil to the seal strips. And then project success. So big, let me put the lights back on. Big project, successful project, and you see those types of wall now all over the highway. I mean, if you drive from College Station to Houston, on 290, you see walls and walls, and these are MSE wall, mechanically stabilized earth wall, the equivalent of reinforced concrete applied to soil. Very, very smart development. All right, so let's switch gear and get back on our discussion about geotechnical engineering. And today I want to talk about effective stress. And you will see that this is actually a very important lecture within this introduction to geotech course, because effective stress is a concept that you do not see in structures, concrete, steel, wood. We don't have this concept of effective stress. So it's very specific to soil mechanics, and so it's an important one. Before I start talking about effective stress, I want to back off and talk about stresses to be sure that we have this well defined. So let's say that I look at the ground surface and I've got a wall, a big structure on that surface, so it's loading the soil. And if I pick a random point, M, anywhere in the mass, there are stresses. Stresses because of gravity, of the weight of the soil. There are stresses because of the big building that you've put on it. And at that point M, there is a resultant force, you know, a single force that is actually applied at M. So if you think of the force that is exerted at M, and it might be in this direction, the stress is defined as the limit of the force divided by the area as the area becomes very small. So the stress, if you wish, and the stress tensor, we'll just put it as F divided by the area. So you have to choose an area to go from the force to the stress. Now, how many areas can you conceive that go through M? Well, there's all kinds of planes. You have to have a plane, and because there's an infinite number of planes that go through M, there is an infinite number of stresses associated with a point. Now, so we said that we can, if we choose a plane, let me put it right here, and I'm going to put it, let's see, I'm going to put it this way. All right. So I'm exaggerating the scale of the plane, but that force divided by that plane gives me a stress tensor, a stress vector. And the stress vector, I can decompose it into a shear stress and a normal stress. Okay? So I've got sigma and tau. And so sigma is going to be the normal stress, because it's the component of the stress vector that's perpendicular to the plane that I chose, and then the shear stress will be defined as the component of that vector in the plane, in line with the plane. So you can always decompose this stress vector into a normal stress and a shear stress. So, you know, one question on the midterm could be, how many stresses are there at one point? And the answer is infinity, because you have so many planes that go, you have an infinite number of planes that go through one point. Then you start thinking about principal stresses. All right, so principal stresses, while we're here, might as well talk about those. Principal stresses. What's particular about principal stresses? Well, they are normal stresses on planes where the shear stress is 0. So in other words, and you can see that if I rotate that plane in a certain fashion, I can get to the point where there is no shear on that plane. So these are principal stresses. So they're typically sigma 1, sigma 2, and sigma 3. Because there are 3 such planes where I can find normal stresses associated with 0 shear stress. So another question might be, how many principal stresses are there at one point? And the answer is 3. But remember that principal stresses are normal stresses. All right. So this is background on stresses at one point. Let me now move to talk about effective stress. So I'm on page 252. What we're going to do, we're going to take a piece of soil and we'll take it at the surface to simplify. Now we're going to take a piece of soil and we're going to cut it down. We're going to do a free body diagram. And we're going to, at the bottom of this piece of soil, you have some grains. And I'm going to zoom in, I'm going to make them big, but they could be extremely small, right? So you have one grain here, one grain there, and another grain here, okay? And I'm cutting through plane that goes through the bottom of these grains. And then I cut vertically on either side, and so my free body diagram is right here. My free body diagram is this piece right here, the solid piece in the center. When you create a free body diagram, you have the right to make it any shape you want, but whatever other piece you remove, you have to show the external forces that that other piece was contributing or acting upon the other material. So what forces do you have in there? Well, you got a force Q, a load, let's say Q, that's coming down, all right? And things are in equilibrium, so we don't have lateral forces. We may have forces on this side that cancel with that one, but we're going to aim to write vertical equilibrium in this case. All right, so we have a number of forces at the bottom because I took out the piece at the bottom. What are those forces? Well, first of all, I have the contact forces. So I might have had another grain that was touching this one. So right here, we're going to call this one F contact, little f contact. And this might be F1 contact. I've got another one here, and let's say another one here that's in contact, okay? So these are the forces that are transmitted by the bottom part through the grains. Then I have water between the grains, and I actually cut through the water when I did that cut to get, so we would have as well some forces, little FW, that were transmitted from that water below to the water above because the water was under pressure or under stress. Okay, and here I also have other little f sub w, so FW1, FW2, FW3, and so on. And then I cut through air as well because I had to do this in the general case, and so I have to assume that the soil is unsaturated. And so I would have, in addition to this, I would have some forces that would cut through the air, and these would be little f sub a. Now I want to write vertical equilibrium. So I'm going to write that Q is equal to the sum of all the forces that are at the bottom. So that's going to be sum of the contact forces, FCI if you wish, from 1 to n, plus sum of FWI from 1 to m, because there may be more cuts, and then plus sum of FAI from 1 to p, let's say. And now I have the three contributions from the grain, from the water, and from the air to try to resist and balance the value of Q. And then I'm going to divide by the projected area, so projected area, that I will call A total. So I'm going to do Q divided by A total equal sum of these 4 FCI divided by A total plus sum of FWI divided by A total plus sum of FAI divided by A total. Now, this I'm going to call the total stress. And I'm going to use the symbol sigma. This I'm going to call the effective stress, sigma prime. So remember that the effective stress is the sum of the forces transmitted through the grains divided by the total area. It would make a lot more sense, to me at least, to divide the force that's transmitted through the grains divided by the area of contact between the grains. That's not what we do. And in good part because we don't know exactly what that area is. It's very difficult to calculate precisely. So we say, oh, what the heck with this? We're going to take the total area. So we do something wrong, but we do it consistently wrong. So and that's how we can talk to each other and do some calculations. And so that's going to be sigma prime. And then here, the FWI, I'm going to express, FW is the force transmitted by the water. So it's the stress in the water times the area through which I cut the water. So I'm going to, this is the stress in the water, we're going to call this U sub W I times AWI divided by A sub T. And then I do the same for the air. Sigma of stress in the air, I, times area through the air, I, divided by A total. Then I note that UWI is simply a constant because I'm at the same level. And so if you think not just hydrostatic, but being at the same level in the soil, then the water pressure is going to be the same on the horizontal plane. And then, therefore, this UWI is going to come out of the summation sign, and sigma of AWI is going to be big AWI. Then, same reasoning for this, UAI is actually a constant through that level. So now I can rewrite the equation as sigma equals sigma prime plus UW sum of AWI over A total plus UA times sum of AAI over A total. I said sigma of AWI is equal to big AW. So that's the entire area. Out of this AT here, I have a certain percentage that cuts through the water, so I'm going to call this AW. And then I'm going to call, by the same token, AAI, I'm going to call this big A sub A. So area through the water, area sub. And then I'm going to note that A total is equal to A contact plus A water plus A air. In other words, when I cut with this plane at this level, I cut through the contacts, I cut through the water, and I cut through the air. So when I add up the area of the contacts plus the area of the water plus the area of the air, I got the total area. This area of contact here is very small compared to the area of the water and the area of the air. Okay, so we're going to neglect this one and say that it's approximately 0. We are going to define, so you see that now right here I have AW over AT. I'm going to call alpha equals AW over A total. I'm going to call beta equals A air over A total. And you can see that from this equation, if I divide by A sub t on both sides, I'm going to have alpha plus beta equals 1. So then alpha plus beta equals 1. So when I go back to this equation here, I'm going to write it here. then I write that sigma is equal to sigma prime plus alpha UW plus beta UA. Okay? That's very important. You can be darn sure you're going to get that question at the midterm. Okay? What is the expression of the effective stress? And I remember as a student, the prof presented it, well, it was a simpler version because we were dealing at the time, 50 years ago. We were dealing with saturated soils, okay? So we didn't have the air in there, and the alpha was 1. We'll come back to this. And so you would say sigma equals sigma prime plus UW, and then sigma prime equals sigma minus UW. And that messed me up because I didn't know if it was plus or minus. Just remember this. This is the total stress, therefore you got to add everything else on the other side. But if you wish to express the effective stress, then it's going to be sigma minus alpha UW minus beta UA. Okay. Now, let's look at different cases. If you have a situation where you have a soil like this, where the soil is saturated. So here, S equals 1. You got water in all the pores, no air. That means this is out. And that also means that AW is when I cut, then there's no air, so AW is equal to AT, and alpha is equal to 1. So in the case of saturated soils, alpha is equal to 1, beta is 0, and the equation comes back to sigma equals sigma prime plus UW. Okay. And that's the equation that Terzaghi developed a long time ago, 1925 or so, and because he was dealing with saturated soils. If, on the other hand, so I guess here we'll put, how did I do that? Water was green, all right. So that means that everywhere in there we got water between the grains, and all this is water everywhere, saturated. Second case, we have a material, oops, so the soil is right here. We still have all the grains. And now we have unsaturated soil. However, the unsaturated soil is such that you have water everywhere in the pores, like this. And you have occluded air, bubbles. So the air is starting to come out of solution, if you wish, and then you have bubbles. So that means that the air here is surrounded by the water. And if it's surrounded by the water, there's equilibrium of stresses, and then UW is equal to UA. And so we have sigma minus alpha UW minus beta UW. So therefore, alpha plus beta UW. But alpha plus beta is 1. So again, in this case, an occluded air, let's say S is less than 1, but higher than 0.85. About 85%. 85% to 100%, typically the air will be occluded. So again, in this case, we've got sigma equals sigma prime plus UW. Third case, we now have The soil, same thing, particles. And the degree of saturation is now less than 0.85. So the air is no longer occluded. But what that means, if the air is no longer occluded, that means you have a free air path all the way to the surface. And at the surface you have atmospheric pressure or zero gauge pressure. So that means that yes, you do have water still in there, green, but you have a continuous path of air all the way to the surface, something like this, if you wish. Okay? So then, in this case, if the air is connected to the surface, then UA is 0. And if UA is 0, we're left with the equation sigma prime, sigma, the way we've been writing it, sigma equal sigma prime plus alpha UW. So you see that here again, did I do that right? No, I didn't do that right here, because if you have occluded air, let me see for a minute here. No, that's correct. So you have a more compressible void phase because of the air bubbles, but you still have this. So in essence, in all cases, you're covered if you remember this one. This is the, I mean, personally, I prefer to look at it this way, as the general definition of the effective stress. And, but this one, and we'll write it in parallel here. So this one always works. For the reasons that I described here, this one always works as well. All right? So we have this. So you need to remember this. Okay? Again, effective stress is a normal stress. So sigma prime is normal stress. Now what happens in the shear domain? If I were to shear on this plane, I've got the grains to grain contact, and that's going to provide resistance to the shearing process. I'm going to also shear the water, but the water has no shear resistance, or it does, but it's so much smaller than the resistance that we can generate at the grain to grain contact that we will neglect the shear resistance of water. Now, if water didn't have any ability to generate shear, we wouldn't have soil erosion, for example. Okay? Or if you jump from a 10-meter high board into a swimming pool and you don't know what you're doing, you're going to hurt yourself because of the shear resistance of water. So it does have shear strength, if you wish, but compared to the soil grain to grain, it's very small. So we're going to neglect that, and therefore the equation for the shear is going to be tau prime equal tau. So there's no correction to be done, or no difference between an effective shear stress and the effective shear stress and the effective and the total shear stress. The total shear stress is equal to the effective shear stress. but the effective normal stress is not equal to the total normal stress if you have water in the material. Now, if you have dry sand, you're on the beach, you got dry sand in your hand, the total stress is equal to the effective stress. Why? Because we don't have any UW. We have UA, but UA is 0, and so therefore at the beach you have sigma prime equals sigma. But in the general case, this is the one that will be necessary to use. All right. In the last 10 minutes, I want to do a problem. Because one of the first steps in the design of any structure, geotechnical structure, you have to calculate the stress profile before you put the structure and after you put the structure. The structure is going to increase the stress, and so the stress is going to change in the soil, and that's what is going to create the settlement, the failures, and some of the things we've talked about in the case history. Now remember, the wall went down 20 centimeters because the stress was significant in the material below, and that's why the wall settled that much. All right, so I'm on page 276. And I'm going to do problem 10.15. So page 276, problem 10.15. All right, so we have a soil profile. The soil profile is ground surface, and then we have a layer of clay which is saturated. So clay, S equals 1. And below that, that layer is 2 meters thick. Below that, we have a layer of sand. And which is 4 meters thick. So we have a layer of sand here, 4 meters thick. And the groundwater level, if you drill a hole in the ground, there's a point where you find water, unless you're in the Sahara Desert. But the groundwater level is at the boundary between the clay and the sand. One more thing, we need the unit weights, and the unit weights are 18. Gamma equals 18 kilonewton per cubic meter in the clay, and gamma equals 20 kilonewton per cubic meter in the sand. And the question is, draw the stress profiles for this case. So the way we do that is we go next to the profile, and we're going to do a profile of sigma, the total stress, as a function of depth. And we're going to call this one sigma 0, meaning before anything happens, geostatic stresses, and V for vertical. So that's the vertical stress. We're calculating this one. And then we're going to calculate, and it's always a good idea to go in that order, we're going to calculate UW, the water stress. Remember that this is saturated by a capillary action. We'll talk more about this next time. And then this is also saturated because it's below the groundwater level. So the whole thing is saturated. It's a simple case. So there will be water in that case. And then we're going to calculate sigma prime 0V. Oh. And we're going to do the calculations at the boundaries, meaning ground surface, separation between sand and clay, and then the bottom here. All right. What is the total stress at the ground surface? Well, there's nothing on top, 0. So we're right here. What is the total stress at the bottom of the clay layer? Well, we have 2 meters of a material that weighs 18 kilonewton per cubic meter. So that means this number here is 2 times 18 or 36. So this is in kilopascal, kilonewton per cubic meter. Everything is going to be in kilopascal here. And then, what is the total vertical stress at the bottom of the sand layer? Well, I've got 2 meters at 18 plus 4 meters at 20. So therefore, that's 36 plus 4 times 20. I've got 80, so 116. 116. And then the profile will be something like that. Well, that's the total stress profile. Let's do the water. Well, the water pressure at the ground water level, it's like the surface of a lake, if you wish, in there, but it's a lake that's buried in the ground. So the surface of the lake, you've got 0 pressure, and so we will, let's put it in like this. So right here, we're going to have 0. And then, what is the water pressure at the bottom of the sand layer? Well, I've got 4 meters of water under hydrostatic condition. So that means that right here, I've got 4 times 10. We'll take the unit weight of water as W equals 10. I don't know what I took in the book, maybe 9.81. But let's take 10 to simplify. So here, I'm going to have 4 meters of water. So this is going to be 40. And I got this. Now what happens and we'll discuss this in the next lecture, what happens in the clay is that you have very small pores. Remember, the clay particles are extremely small. As a result of this, the water is attracted into the pores, and we have water pressure in the pores. The material is saturated by suction, by capillary action. And this capillary action extends to extend this line. So we've got 20 meters of suction. So the water essentially is pulled up all the way to the top of the clay. So the water is in tension here, okay? UW negative. And then here, UW positive. The water is in tension here, but I'll explain the phenomenon of why the water wants to go up into the clay layer. So here we're going to have minus 2 times 10. And then sigma prime OV is going to be sigma prime OV equals sigma OV, we're back here, minus alpha UW. And alpha is 1 because the soil is saturated. You see right here. So therefore, minus UW. And so we have 0 minus 20 plus 20. Here we have 36 minus 0, 36. Here we have 116 minus 40, 76. And here is the effective stress profile for this simple case. All right? So next time we're going to start discussing this issue of having tension in the water, the capillary rise, and so on, because it's critically important to understand how unsaturated soils behave. And unsaturated soils in our business cover a tremendous percentage of the cases that we deal with. Okay, I'll see you next time.